After such a long presentation last time, this one here should be nice because it is mostly printed up for you. I believe it's only slide 3 here that you need to jot down. These other things I'm going to have printed for you already. But last time we talked about electric current, which is moving charge, but we didn't talk about where the charge is moving to or from. And usually that happens within a thing called a circuit. And so we're going to look at the electrical circuits here. The big difference between the past and now is in the past you've built circuits, but you've not really done the math with them, and we're bringing all the math in here. So somewhere in elementary you had electric circuits introduced to you, and we're not going to move much beyond what you did back then in terms of the types of circuits we build, but we are going to add in a lot of math to it. Anyway, the schematic symbols you should have printed for you. One thing I will point out is these are only semi-standard, and so they do change, although having said that, most places use the same ones. So we've talked about resistors. They're the zigzaggy line. Capacitor has a curve and a straight line. Sometimes one side is specifically positive or negative, and that might be labeled. Certain types of capacitors it matters, others it does not. Meters are usually, and this is semi-non-standard, but usually a circle, and then the type of meter will be labeled with a V, A, G, or M for voltmeter, ammeter, galvanometer, and multimeter. Wires are lines. Unconnected wires will just cross. Sometimes they'll bump them up over to show that they cross, but actual connections will have dots drawn in bold there. Diodes will usually be a darkened triangle pointing one way. It turns out the diode's current only flows in one direction and doesn't flow the other way, so there's a stop on one side that says that it doesn't flow through. Also, light emitting diodes, or LEDs, have the same symbol, though sometimes they'll show little arrows to show that these give off light, or put them in a circle to show that they give off light. Switches usually look like a switch, and this switch here is shown to be open. If the line was down, it'd be closed. Batteries are usually a long line and short line. A lot of times each pair of long short will be used to represent 1.5 volts, so again, that's not always true. Ground is usually this symbol here. It's kind of like a triangle made up of shorter and shorter lines, and then this thing over here that looks like a filament, an old-fashioned filament, is sometimes used for a light bulb. Those are about all the symbols that we're going to use with the circuits we're going to build, and you will be asked to draw and read a few schematics. Those are how I draw all of mine. Again, there are some exceptions. There are a ton of other symbols that we're not getting into. If you are interested, the Electric Circuits Quarter Project is a great way to get involved, or you can talk to me, and I'm a hobbyist in electronics, so I'd love to share more. Anyway, moving on. This is the only slide, as far as I know, that you actually have to copy down. But a circuit is any complete path, and by path we mean a loop, and by that a closed loop. It does not have to be circular at all, but any complete path along which charge or current can flow. A schematic is simply a diagram, usually that engineers, electricians, etc. Use to show the electric circuit, and it uses specialized symbols just to clean it up and make it easier to read. We could draw what the circuit physically looks like, but it's a little bit easier if we draw it as a schematic. And most of the schematics we draw will be fairly easy to read. There are some out there that are difficult just because they're big or because the connections aren't super obvious. Anyway, there are two basic types of circuits, and you've seen these in the past back in elementary, but a series circuit is a circuit where the charge flows through each device in turns. That is, it goes through device A, and then device B, and then device C, and so on and so forth. And if it's broken anywhere in the path, then the whole thing goes dead. Versus parallel circuits, or circuits where the devices are connected in such a way that the 2 points connect to the power source. That is, every object, sometimes groups of objects, are powered individually. And so that is a parallel circuit. A couple examples of this. Christmas lights, especially the ones with the big old bulbs, used to be always in series. If you took out one bulb or one bulb went dead, the whole strand went dead. Now they're wired in between series and parallel. So you could have an individual bulb go dead and the rest of the circuit will work because that bulb is wired in parallel with the rest. But if you take out a whole bulb because the bypass is built into the bulb itself there, or if you have a section a break in the wires in a section, then the whole strand will get dead. And so there is a series segment to it still, but there's also some parallel bits to it. Another example would be your house. I live in an older house, and if the dishwasher is running and my wife tries to dry her hair, it's guaranteed to break the circuit. There's several other things that will trip a circuit breaker, but tripping a circuit breaker, it will have several things and several rooms go off. They'll shut off. So some lights in the house will work, and other rooms the lights won't work. The rooms where the lights aren't work, they're in series with one another. These things that are all connected, that all go dead on the one circuit, they're in series. But the other circuits are connected to other breakers and are kind of wired in parallel to one another. And so that's another example of the difference between series and parallel. This slide, again, is printed up for you, but it shows you a sample series schematic where one power source supplies object A, then B, then C, versus parallel where the power source applies to A, but also to B and C, all at the same time, and these are all in parallel with one another. And so if one of them was taken out, then the others still work. Whereas over here, if one of them's taken out, the whole circuit goes dead. I have a list here of properties or characteristics of a series circuit, and it includes a whole bunch of formulas. This is printed up for you. Basically, the properties are then described in formula format. A reminder from the past that this giant letter here is the Greek letter sigma. It's their capital S, and it's is used in mathematics to stand for sum of. So for here in a series circuit, the total resistance is equal to the sum of all the resistors. So it's resistor 1 plus resistor 2 plus resistor 3, so on and so forth. Ohm's law is true, is really all these two are saying. Though we can calculate the drop in voltage across an individual item on the circuit. And current is the same everywhere. And so on. Parallel circuits, the properties are a little different. We still have Ohm's law applying to it, but now the currents are additive, and the voltages are equal everywhere on the circuit. The oddest thing about this is the resistance formula, that 1 over the total resistance in a parallel circuit is equal to the sum of 1 over the total resistances. And what that means is that you have to get a common denominator here on your resistances, then add them up, and then flip it, take the reciprocal, to actually get the total resistance in a parallel circuit. Also, there are some capacitor formulas. They're similar, but remember, capacitors are pretty much the opposite of resistors. So the total capacitance in a series circuit looks like the total resistance in a parallel circuit, and vice versa. Also, we have another couple formulas for measuring capacitance, and these also will be printed up for you. If you have any questions, be sure to bring them to class. These formulas will make a lot more sense, though, when we start actually just using them in circuits. When we start building circuits, testing these properties, and then calculating to see that, yeah, they hold.